As mentioned earlier, the software may use Gini index, entropy, or chi-squared test for selecting the best split among the candidate splits. I'll give you a choice of impurity measurement to use. In this illustration, we are going to assume that the chi-squared test is used. You probably remember that to identify the best split, the chi-squared test looks for the split that produces the smallest p-value. Since the p-values can be very small, and that makes it difficult to compare visually, so it is often transformed into another measure called the log worth, which is the negative natural log of the chi-squared test p-value. For example, if we have a significant p-value of 0.001, the log worth is equal to 9.213. And if we have a non-significant p-value of 0.1, then the log worth is equal to 2.3026. The log worth is always going to be a positive number, so the minimum log worth is 0. As the p-value becomes smaller or more significant, the log worth would increase. Therefore, the larger the log worth, the smaller the p-value, and the better the split is to create pure subsets. Now let's look at an example. This is a hypothetical dataset with data points that belong to two classes, yellow and blue. And let's use yellow as the target class, or class 1. And the blue as the non-target class, or class 0. We have two predictor variables, x1 and x2, which can be any numeric variables. As you can imagine, given the relatively large number of cases in this dataset, there are many candidate split points along x1 and also along x2. As of now, half of the cases are yellow and the other half are blue, so the class distribution of this dataset is 50-50. Which is a completely impure dataset. The goal is to create a classification tree that will help us classify future cases into either the yellow or the blue class. This would be difficult to do with a traditional statistics technique such as the logistic regression, as the data does not follow a very clear pattern. Data-driven techniques such as decision trees tend to perform better in these situations. To construct the classification tree, the split search algorithm first identifies all the candidate split points along the variables, which are the midpoints of consecutive values as we discussed earlier. Suppose we start with x1. The algorithm computes the log worth of every partition created by candidate split points on x1. We use this white curve to visually display the log worth associated with all the partitions. As discussed earlier, the larger the log worth, the smaller the p-value, and the better the split is to create pure subsets. Therefore, our best split along x1 is going to be here, because it has the highest log worth. As you can see, our best split point on x1 according to the log worth is x1 equal to 0.52, with a log worth value of 0.95. We can figure out the chi-squared p-value associated with this split point using e, the mathematical constant, raised to the negative 0.9 power, and e is approximately 2.718. So this would give you the p-value of 0.3868, which is not a significant p-value using the threshold of 0.05. This makes sense because if you look at the contingency table displayed in this side, the frequency numbers are not that different from a 50-50 class distribution on either column of the table, suggesting that the subset purity has not been significantly improved by this split. However, that is still the best split on X1, as other splits produce even less significant p-values. So, should we use X1 equal to 0.52 as our first split or the root node for the classification tree? Well, we haven't inspected all variables yet. We still have X2 to inspect. So now let's inspect X2 in the next slide. We repeat the same process of producing the log-worth values for all candidate split points along X2, and plot the log-worth values using a white curve. The highest point appears to be at X2 equal to 0.63 with a log-worth value of 4.92. You can also compute the p-value from the log-worth number, which is e raised to negative 4.92 power, and the p-value equals to 0.0073, suggesting that it is significant at the 0.05 level. This information can also be confirmed by looking at the contingency table, where the frequency numbers show a larger variation from the 50-50 class distribution. After repeating the process for all variables, in our case, both x1 and x2, we now compare the log-worth values of the best splits from all variables. As you can see, the log-worth for the split on x2 equal to 0.63 is greater than the log-worth for the split on x1 equal to 0.52. Therefore, the split search algorithm selects x2 equal to 0.63 as the best split among all candidate splits. As a result, the split search algorithm constructs the root node for the classification tree as you see in this slide. The root node inspects whether x2 is less than or greater than or equal to 0.63. The contingency table in the previous slide also provides us with the probability values for the two branches. If x2 is less than 0.63, then the probability of the case belonging to yellow is 0.46. And if x2 is greater than or equal to 0.63, the probability of the case being yellow is 0.65. If you look at the scatter plot, the split of x2 equal to 0.63 has created two partitions among the cases, a top partition and a bottom partition. The recursive partitioning process suggests that future partitions will be dependent on all previous partitions. Therefore, to continue growing the classification tree, the algorithm will make more partitions within the two partitions in the diagram. Now let's focus on the bottom partition, which corresponds to the branch left, or x2 less than 0.63. We will repeat the process of finding the best split in this partition. Again, we start with x1 to compute the log-worth of all potential splits. As you can see, the partitions are made only within the bottom partition. completely ignoring the cases in the top partition. That is why the process is referred to as recursive partitioning. Among all the candidate split points, we found that the split x1 equal to 0.52 produces the highest log worth, 5.72. The contingency table shows the class distribution with the split. The cases in the left partition have the probability of 39% to be yellow, whereas the cases in the right partition have the probability of 45% to be yellow. Is this the next split on the classification tree? Well, we need to first inspect other variables. As before, we inspect the other variable, x2, to identify its maximum log worth. As you can see from the diagram, the maximum log worth for x2 within the bottom partition is produced by the split x2 equal to 0.02, and the log worth for that split is 2.01. Next, we compare the maximum log worth values of x1 and x2, and find that the split on x1 has a higher log worth value than the split on x2. Therefore, the next split on the classification tree will be made on x1 equal to 0.52. As the split search algorithm continues to partition the data recursively, the classification tree is being expanded gradually. We have now created a second partition rule for the branch left partition. According to the contingency table in the previous slide, the cases with x2 less than 0.63 and x1 less than 0.52 would have the probability of 0.39 to be yellow, whereas the cases with x2 less than 0.63 and x1 greater than or equal to 0.52 would have the probability of 0.45 of being yellow. This process will continue until all leaf nodes are pure subsets, meaning that all cases in the same leaf node belong to the same class or with a 100% probability of being yellow or blue. As you can imagine, to grow the decision tree to have all pure leaf nodes for this dataset will take many iterations, and the final tree will have many levels and be very large and complex. The resulting tree of the split search or recursive partitioning process is called full tree.